She's a
bad thing, fine as hell, thick as fuck. Oh my god.
Hey guys, for today's Chemistry 101, we're going to discuss about redox reactions, carbon dating, enthalpy change, nuclear reactions, and final temperature. For our first topic, redox reactions. Let's get to it. So for our first topic, redox reaction, we have here a sample equation that our goal is to make it into a basic solution. Now first, what we have to do is get the half reactions of each of these compounds. Now let's solve. Now we can cancel this. Now all we have to do left is input it here. 16H. Now you can now subtract 8H2O with the 16H2O. Now where to put the 8H2O? Now we have to put it on the greater side. So it's here on the reactant side. 8H2O. When you subtract, you have to decide where to put that. So on the greater, always put that on the greater side, either on the product or on the reactant. But in this case, we're going to put this on the reactant side because 16H2O is greater than 8H2O. So and then copy the rest of the equation except this one because you already cancelled it. Plus 7 aluminum plus 16OH. And that is your final answer. This is now a basic solution. So for our next topic, nuclear reaction. There are different types of nuclear reaction. There are alpha decays, beta decays, positron emission, electron capture, and gamma decay. Now here are some samples for each decay. And these are the constants for each of the decays. These are the constants for alpha decay, it's a constant for beta decay, this for positron emission, this for electron capture, and finally this for gamma decay. Now let's solve for a problem. In alpha decay, all you have to do is subtract the atomic weight and the atomic number on the succeeding or the reactant side. Now, 72 minus 4 is 68. 15 minus 2 is 13. Now in the periodic table, what element has the atomic number of 13? It is aluminum. Simple as that. Now, for the beta decay, all we have to do is find an element that is one atomic number higher than this because we have a minus 1 atomic number here. So, we have to find an element that has a 37 because it is higher than 36. 37, atomic weight, atomic number, then copy 42 because it's 0, 42 minus 0 is still 42. Now what element is, what element has the atomic number of 37? And that is rubidium. Now for the positron emission, we are going to do the opposite. We have to find a number with a atomic number that is less than 20. A single atomic number less than 20, which is 19. So, what element has the atomic number of 19? And that is potassium. 48 minus 0 is still 48. Now for electron capture, what we have to do is add the single atomic number with here, which is silver. So 47 plus 1 is 48. In the periodic table, what we have there is palladium. Now 68 plus 0 is still 68. Simple. Now for gamma decay, it's just like beta decay. The difference is we have this particle. Now we have to find a element that is a single atomic number higher than 82. So 83. 120 atomic weight still the same as 120 minus 0 still 120. Now, what element has the 83 atomic number? And that is Bn. As simple as that. Nuclear reaction. And now for the next topic. So for our next topic, carbon dating, we have a sample problem here. Archaeologists found that the carbon found on a bone was carbon-14, and it has a decay rate of 2.8 counts per minute per gram of carbon. Assuming the decay rate of the modern jawbone is 14.8 counts per minute per gram of carbon, how old is the jawbone? The half-life of carbon-14 is 5,730 years. Now, to be able to solve this, we're going to use this formula. Being the time is equal to 1 constant over k, which means the decay constant, times ln, which is a constant on your calculator that can be found in your calculator, times k rate, NO over n. Now, let us list the variables available for this problem. So, NO is equal to 14.8 counts per minute per gram. N being the lower decay rate, 2.8 counts per minute per gram. Half-life, which is T 1/2 time. Half-life is this is the unit for half-life. 5,730 years. Okay. So we can't use this formula yet because we don't have a decay constant. So solving for the decay constant is k is equal to ln times 2 over the half-life of carbon -14, which is equal to ln times 2 is equal to 5,730. Now, ln, the ln can be found here on your calculator. ln times 2 divided by 5,730 is equal to 1.22097. I'm just gonna round off this to the 4th digit so we can minimize the number of numerals. Times 10 raised to -4. We're going to just substitute that. We can now solve for the time for the carbon date of the jawbone. So 1 over k is equal to 1.2097 times 10. 2097 times 10 raised to -4. This is 4 times ln times NO, which is 14.8 over 2.8. If we're going to solve that, 1 over 1.2097 times 10 raised to -4 times ln times 14.8 over 2.8 equal to 13,763 years old. And that's the answer for this sample problem in carbon dating. So for our next topic, enthalpy change, we have here a sample problem. Calculate the heat required when 100 grams of ethanol at -178 degrees Celsius has turned into steam at 120 degrees Celsius. Now this is our formulas that we're gonna use for every phase change and just a conversion. And these are variables. We have here the specific melting point and boiling point of ethanol, and this is the specific heat of ethanol in solid, liquid, and gas phases. And this is the specific heat capacity of fusion or melting, and this is the specific heat capacity of vaporization. And this is our mass for ethanol, 100 grams, and our conversion for 1 mole is equal to 46 grams. Now for our first solving, Q1, we're going to use this formula. So M, mass, 100 grams, multiplied by specific heat, which is in solid form first, 0.97 joules per gram Celsius, times change in temperature, which is final temperature minus initial temperature, 120 degrees Celsius minus negative 178 degrees Celsius. Okay. So now we're going to and 6. Now what unit are we going to use? We're going to use joules because mass grams we're going to cancel, and Celsius. The only thing that's left is joules. So that's the unit that we're going to use. Now for Q2, this is actually our first phase change. So for this phase change, we're going to use this formula. So Q2 is equal to, remember our conversion, 1 mole is equal to 46 grams multiplied by the phase, which is melting or fusion, which is 5.02 kilojoules per mole, times our mass, which is 100 grams. (10.91 kilojoules), or if you're going to convert kilojoule into joule, just multiply it by 1,000. So move the decimal value 3 times. You're going to have 10,910 joules. And now for Q3, we're just going to use the same formula just like before. So 100 grams times, but this time its phase is in liquid form. So 2.3 joules per gram Celsius times change in temperature, which is 120 degrees minus negative 178 degrees Celsius. So if you're going to go 68,540 joules. Remember to cancel this. We're not going to use that anymore. The only unit left now is joules, so that's the unit. So for Q4, that's your second and last phase change. And for this case, we're going to use vaporization. So instead of 5.2 like we used here, we're going to use 88.6. So our conversion, 1 mole equal to 46 grams times 88.6 kilojoules per mole times our mass, which is 100 grams. Just take note of that. So cancel, 192.61. 2 decimals, so we don't have too much value, or 192,610 joules. For our last phase, not a phase change anymore. I mean Q5, not Q4, Q5. Same formula, just like in Q1 and Q3. We're just going to do the same process, but this time it's in gas form, because here our ethanol vaporized in Q4. Now it has become in gas phase. So 1.94 joules per gram degrees Celsius times times 120 degrees Celsius minus negative 178 degrees Celsius. Okay, 57,812 joules. Cancel all these joules. Okay, for our final answer, we're going to add Q1, Q2, Q3, Q4, and Q5. Now, and the answer for that is equal to 358,778 joules. And that is our final answer. Thank you for listening to our chemistry class for today, and I hope you learned a lot.
She's a bad thing, fine as hell, thick as fuck. Oh my god, that's my babe.